Good day. So in this video, we're going to talk about programmable controller and we'll try to simulate some using the application software Automation Studios. So, first things first, a programmable logic controller is an industrial-based PC consisting of a power supply, a CPU, which execute programs, processes input signals, and control output devices, an input module, which interfaces sensors to the PLC, and output modules, which controls the load devices. PLC was designed to perform logic operations, timing, and counting functions, sequence control, data manipulation, analog and digital signal processing, and networking that completely replaced the electromechanical relays. So for this activity, we were tasked to make a PLC ladder diagram that have 3 switches, S1, S2, and S3, and a lamp. The lamp can only be switched on by pressing any 2 switches. So, here is the PLC ladder program that I have created out of those given conditions. This is how the PLC ladder program looks like in Automation Studio. To simulate this program, we will try to run it at normal simulation. You can observe that when one switch changes state, the lamp does not turn on. Like what the initial conditions given. While when two switches are on, we can see the light turning on, the lamp turning on. Now, the second PLC ladder diagram has the following characteristics. Lamp A turns on when PB is pressed, even when released. The same thing happens to PB2 in controlling lamp B, which lamp B will only be reset by PB3. The first PB to be activated will disable the next PB until PB3 resets the system. Write the corresponding PLC ladder diagram. Out of this initial condition, this is the PLC ladder program that I have deduced and simulated. In Automation Studio, this is what the PLC ladder diagram looks like. Now, we're going to simulate and prove whether this circuit diagram met the initial conditions. So, in the initial condition, it's stated that when PB1 is pressed, the lamp A will turn on. Same thing with lamp B. When PB2 is turned on, lamp B will lit up and will close or turn off lamp A. Now, the system will reset when the push button 3 is clicked or pressed. Now, this setup, we can observe that the initial conditions or the criteria in making this PLC ladder diagram successful was met. Thank you, and see you in the next experiment. Bye! Good day! So in this video, we will try to talk about PLC timer and counter. In particular, we will try to simulate some diagrams or programs in the simulation software Automation Studio. In this activity, we were tasked to design the ladder diagram with the following initial conditions. With 1 being lamp 1 turns on once start is pressed. B. After 2 seconds, lamp 2 turns on. C. After 2 seconds, lamp 3 turns on. And D. After another 2 seconds, all lamps will turn off. Pressing start again will repeat the sequence. With these given conditions, the PLC ladder program that I have made that I think satisfies the conditions is this one. In Automation Studio, this is what the ladder program looks like. Now, to simulate, we will be simulating the file at normal simulation. So, according to the initial condition set, lamp 1 should turn on once the start button is pushed. And then lamp 2 and lamp 3 will turn on after 2 seconds. And after that, the sequence will start again. We can see that the presented ladder diagram on the screen satisfied the conditions given by our professor for this activity. Now, for the second simulation program, we were tasked to create a counter simulation for a brewery plant. With the conditions, a momentary no contact push button is pushed to select which kind of beer to produce. First, on selects beer 1, second, on selects beer 2, third, on selects B3. Fourth on shall reset selection, all outputs are reset. Cycle continues depending on number of ons on the push button. With this initial setup or conditions, here is the PLC ladder program that I have created. Now we will try to prove or disprove this circuit diagram in the simulation software Automation Studios. Presented on the screen is the ladder program in Automation Studio. Now, we will try to simulate it under normal simulation. So switch 1 chooses beer 1, on 2 chooses beer 2, on 3 selects beer 3, and the fourth one resets the whole program. So once again, when we click the on button, the push button, first it will select beer 1. When we press it again, it will select beer 2. And when we press it again, it will select B3. And for the fourth press, the program will reset. The third program that was tasked to us to make is a timer and counter simulation, which implements the process with the following specifications. First, a start button shall be used to start the sequence. No two motors are turned on at any given time. Motor 1 shall be turned on once start is pressed. After 2 seconds, motor 1 is turned off, then motor 2 is turned on. After 2 seconds, motor 2 is turned off, then motor 3 is turned on. After 2 seconds, motor 3 is turned off. After 3 continuous cycle, the process resets. Pressing start will begin the process again. So with this, here is the PLC Ladder program that I have made, which we will try to prove or disprove in the simulation file I have created in the Software Application Automation Studio. Here is how it looks like in the Software Application Automation Studio. Now we will try to simulate it and identify or verify whether the circuit diagram actually meets the criteria or the conditions given. So we will simulate it under normal simulation. It said that once start is pressed, motor 1 is turned on. After 2 seconds, motor 2 is turned on. Motor 3, the same thing with motor 3 after 2 seconds, while motor 1 and motor 2 turns off. After 3 continuous cycle, it should stop. The program stopped after 3 cycles. So let us observe the ladder program again and count the cycles it produces before it resets. First cycle. This is now the second cycle. We are now on the third cycle. And after the third cycle, the program stopped. So that's it. We can say that this ladder program satisfies and meets the criteria or conditions that was given to us by our professor. And I think that's about it. Thank you all. Bye.